This is the first lecture of Chapter 17. We're going to look at the principle of linear superposition, and that's a fancy term for looking at constructive and destructive interference of waves. When two or more waves are present simultaneously at the same place, the resultant disturbance is the sum of the disturbances from the individual waves. So we're gonna look at what this means and what this means in terms of light waves and sound waves today. Let's start off by looking at the constructive and destructive interference of two pulses along a slinky. This will help us understand how sound waves or how waves act with sound and with light. So if you look at this first picture here, we have two waves coming at each other. The overlapping begins, and what happens is when they superimpose on top of each other, you'll see that there's constructive interference. They actually are on top of each other, they build up, they add up, and they have a bigger amplitude together. But then they continue through each other unaffected. You'll see that this wave that was on the right-hand side is now over here on the left-hand side, still going to the left, and this wave that was over on the left is now over here on the right, still going to the right. They pass through each other unaffected. But when they're superimposed on top of each other, they have a larger amplitude. In this second case, what we have here is two waves coming at each other, but one's a crest and one's a trough. When the overlap begins, they are separate from each other, but you'll see when they are on top of each other, since the two amplitudes were the same before, you'll see that the total amplitude right now is 0. That they overlap on top of each other and you have destructive interference, but then they pass through each other unaffected again. Now we're going to go ahead and take a look at constructive and destructive interference of sound waves. So if you had two speakers here, and one speaker is giving off a sound wave and another speaker is giving off a sound wave, they'll start overlapping each other, and you'll have areas of constructive and destructive interference. Here we have water dripping from a faucet into some water underneath. And this one faucet, you'll see these waterways from the top. You can see that the dark lines are the troughs and the bright lines are the crests. Now if we start the other one dripping as well, what will happen is it will now start sending water waves out, and you'll have areas of constructive and destructive interference. And you'll see right along this area here is area of destructive interference. The water is actually flat. And an area here you'll have constructive interference where the wave is where the wave has actually increased its amplitude. Alright, now we have this detector here that I'm going to place at different points. So we can see right here in the middle, there's constructive interference. You can see that the waves are very high, the amplitude is very high. So we notice that where there's constructive interference, the amplitude of the wave is very high. And where there's destructive interference, we'll place it right there. You'll see the amplitude dies out. That's where the destructive interference is occurring. And that you can see where the line of that occurs. It's all the way along there. If I get it right in the right spot, there's destructive interference. And if you go over here, there's very high constructive interference. So all along this line here, there's constructive interference, and all along this line here, there's destructive interference. And that's what architects have to worry about is dead spots in the dead spots in an auditorium. So they try to put the walkways where the dead spots would be, and so on. So this is for waterways, but you can do this for sound waves as well. Here we have two speakers going at the same time. You'll see a very similar situation with these sound waves. It's the exact same thing. Right there, there's destructive interference. So I put my detector there. Here's constructive interference. Put my detector there. Destructive, constructive, destructive, constructive. So you can see these lines right in here of destructive interference and these lines of constructive interference. And you can also see this for light as well. Here's if we have two lights going, you can see the exact same thing happens with light waves as well. You have destructive and constructive interference. As a matter of fact, if you put a screen up in front here, you'll see the screen. You'll see an area of constructive interference on the screen, an area of destructive interference on the screen as well. Alright, so I'm going to send these two waves towards each other, and we're going to see what kind of interference occurs. They start and they come at each other, and there should be some kind of, we see this constructive interference. It goes up and over. And let's go ahead and try it reverse, where we do destructive interference. So we'll now run this, situation. And we'll see it's destructive interference. The two will come at each other, and the black line will destroy itself. And then we'll go ahead and we'll just go ahead now and do some other shape here. We'll try this shape here, a little interesting shape, see how it looks when it goes by each other. Destructive interference, but it's going to be an interesting, won't be total cancellation out of each other, but it'll have some kind of strange shape there. If you want to go to this website, look at this website up on top and try a few shapes yourself, feel free to do so. Now we're going to take a look at a problem, how to solve a problem in terms of constructive and destructive interference. And we say in figure 17.7, two in-phase loudspeakers, A and B, are separated by 3.2 meters. A listener is standing at point C, which is 2.4 meters in front of speaker B. The triangle ABC is a right triangle. Both speakers are playing identical 214 hertz tones, and the speed of sound is 343 meters per second. Does the listener hear a loud sound or no sound? In other words, is destructive or constructive interference occurring right here? So I want you to think about this. How are we going to figure out if destructive or constructive interference occurs right here? So pause the video, think about that. What we're going to do is we're going to find out if a crest meets a crest, or a crest meets a trough, or a trough meets a trough down here to know if it's destructive or constructive interference. We know speakers A and B have the exact same frequency, which means they have the exact same wavelength. It says up here that they're in phase, so when a crest leaves A, a crest leaves B. So what we have to do now is figure out, well, how many wavelengths occur along this 2.4 meter line, and how many wavelengths occur along this line. We haven't calculated that, but that's just the hypotenuse. How many wavelengths occur here? And so what we say to ourselves is, all right, if they are half a wavelength difference, then it's destructive interference. If there's a multiple, is an integer number wavelength difference, it's constructive interference. So the first thing we want to do is let's figure out what this distance is right along here, what the hypotenuse is. And so let's use the Pythagorean theorem to calculate that. So we find out that this distance right here is 4 meters. And now what we want to do is figure out what the wavelength is. So we're going to have to use the equation velocity equals frequency times wavelength. Let's go ahead and we know that the velocity is 343 meters per second. We know our frequency is 214 hertz. And we want to solve for that wavelength. So if we calculate that, our wavelength ends up equaling, so we end up with 1.6 meters for our wavelength. So we want to see how many waves occur along this 2.4 meter line, how many waves occur around this 4 meter line, and we'll be able to see if we have destructive or constructive interference. So if we look at the 4 meters first, we'll take the 4 meters divided by 1.6, and we'll end up with 2.5 waves along this 4 meter length. And let's do the same thing, but now for the 2.4 meter length. So for that section, we end up 1.5 waves. So what happens is from here to here, 1.5 waves fit in. And from here to here, you have 2.5 waves fit in. Now, if they're in phase, so let's say you start with a crest here and you start with a crest here. If you start with a crest here and you go 1.5 waves, what you end up with is a trough down here. And if you start over here with a crest and you go 2.5 waves, what you end up with down here is, starting off with a crest, you end up with a trough down here. So since you have a trough and a trough, you actually have constructive interference occurring at this point. You have a trough meeting a trough, and so the noise actually would be louder at that point. So this is the way we can go about solving for whether constructive or destructive interference occur. You'll notice that this is 2.5 waves, that's 1.5 waves. The difference between the two waves is a multiple, is an integer number. 2.5 minus 1.5 gives you 1. So you know that if you did 2.5 minus 1.5, you would get a multiple number, a difference of 1 wave between the two. That will always give you constructive interference. Now, if it's half a wave difference between the two, then that would end up with destructive interference. And that's not what we have here, but that's just how you would know if it's destructive interference at that point.